5 pages of run over and appendices.
Should we start?
And
Yeah,
then,
go for it.
Those,
Okay.
those are then selected according to points. We award.
Hey everyone.
Oh, sorry. Do you have
Hello.
a-
Hi. So I'm Julien, and this is Matthieu. We founded Dynamik Orbits 4 or 5 years ago, and what we do at Dynamik is to model or design satellite constellations. Usually our customers ask us questions like, what will Starlink be in 5 years or 10 years, or where to position ground stations on Earth to serve this or that constellation. We're going to talk today about Marslink, which is a project that companies might be interested in to connect Earth and Mars with a high data rate, the high throughput, let's say 1 gigabit per second connection between Earth and Mars. Not just for Earth and Mars, but also for spacecraft traveling between those two planets. So this is not synced here. Let's try and resolve.
Let's see if I can fix it here.
Yeah.
There we go.
Okay, let's try it again. Okay. So the goal today is to give you an overview of Marslink, the way that we envision it, because we don't know what it's going to actually be. We're just, imagine it if we were going to build it, and share a few findings. The agenda is, first of all, why. Second, the Earth-Mars communication paradigm so far. 3, heliocentric design options. So what are the different options of design? Then what design would we choose for 1 gigabit per second? And finally, the costs. So the why, there's different ways to answer this question. First of all, obviously it's useful if we have a colony on Mars or even just robots to have an internet connection that is robust and that is high bandwidth. And as I said, also for spacecraft traveling to and from Mars. So, as this reality occurs, it will become very obvious that this is needed. The other way to answer the why question is, why did we do it? Because we did not have a customer asking us to do it. So first, I need to take just a few 1 minute to talk about my wedding, which was 10 days ago. And the reason, thank you very much.
Congratulations.
Thank you. The only reason I mentioned it, I would never do this at a conference, of course, but the theme was Mars. That was our wedding theme. So I thought you might just want to see a few pictures. So this is my beautiful wife, Cécile.
Grooms are from Mars.
Yes. This is this SpaceX Starship rocket with the flame, next to the wedding cake. Here we made special champagne bottles with the Mars label, which we designed. And so our guests were really surprised, and that was pretty awesome.
Next year, you bring a picture of the baby.
Yeah, that would exactly the Mars baby. I have 2 more slides of this, and then I'll go back to business. This is me here flaming some marshmallows, not marshmallows, for some interplanetary s'mores. This is an app I made for the wedding. There's a bunch of useful things that you can do with the app. Here I'm just showing one screen where you can see the people at your table, the other tables here, and the venue was actually a big Mars map.
Oh my God.
So there's Olympus, Mons, Solis Planum, Utopia Planitia, like all the actual locations. And if you move, you have the 2D map with the little rover showing you you're getting close to your table. So Olympus, Mons obviously is like to the west all the way, things like that. And here it shows you that these passengers are checked in the interplanetary flight to Mars. But I was not, because the guy at the venue took my phone away because it was like, I know you're coding all the time, so you can't do that. And that's some information about Mars, like scientific data and things like that, to help people understand better. And the last one is the cocktail bar, which is the Green Hub cocktail bar. So with some basil and things like that. Next drink, 1.5 AU, but this is for astronomically unreachable, not the normal unit. Oh, and the last thing, and then I'm done. This is Visit Mars. So you had a few, what do you call them, the little meteorites from Mars and you could actually look through the microscope.
Right.
So our guests were like, they were like, what did you guys do? We can't believe it.
It was a very special experience for the guests. I guess.
Yeah, Matt was my best man, so thank you very much. Okay, back to business. The reason that we got excited, I got super excited when I saw this tweet. This is NASA saying we want to have a connection that's 4 megabits per second or more between Earth and Mars, and a few companies responded, and SpaceX actually wants to have 1 gigabit per second. So when I thought about that, I'm like, we need to model it because it's not very easy to do. So that's, on that day, I dropped everything I was doing and I focused on this for like 2 weeks straight, just to tell you how crazy I am. Anyways, next point is going to be the Earth-Mars communication paradigm. Matt, take it away.
Yeah, thank you, Julien.
So Matt, just before starting, I wanted to just show you a very simple slide, which is just talking about the evolution of the internet connections on the Earth and in space. And I mean, over the last few decades, we've gone from a few kilobits dial-up to a few megabits, and now we are above 100 megabits. That's the global average connection speed that we experience, and some people are already, of course, much higher than this. In terms of deep space communication, it's not the same. It's roughly the same low, right? Just not the same exact angle, but really we've gone from S-band and very few kilobits per second to a few megabits per second, and then with some X-band and K-band, and then more recently with Psyche, there was demonstration much higher bandwidth. I've normalized everything at 1 astronomical unit here, but basically this is the way we're moving. So effectively, NASA is asking for above 4 megabits per second, which is kind of what we're working with at the moment. And the goal should be, in the next few years, to get to 100 megabit, and of course in a few decades, or 1 decade, to the 1 gigabit per second. And I'm always going back to this because it's actually it's always something that I struggle with. But it's we're working with scaling laws in communications everywhere, but in space it's really where we feel the pain of those scaling laws. And so basically, this is the free space path loss is really what we are fighting against when we're trying to connect to a very distant destination. And I mean, the basic issue is that the power spreads, as the waves expand when you're traveling, and that loss is increasing with the square of the distance. So you'll get this very, very dramatic increase in loss, as you move away from the Earth. And just as showing you, there were multiple on the Psyche spacecraft in optical communication in laser. There were multiple points that were made and measurements that were made at different times during the transit of the spacecraft, and of course it follows that scaling law. So I mean, this is the same issue that you have if on this very simple representation of the solar system with the Earth and Mars. If you want to move data at a high speed between those two distant situations or location, you start with a gigabit per second from Earth. You can see very easily, I mean, it's just illustrated, that you can't even reach half the distance between Earth and Mars and get more than 1 megabit per second. So obviously you need relays, and that's where you put some relays. But of course, orbital mechanics does not allow us to put relays between Earth and Mars in that simple fashion. And that's where comes the question: okay, what is the architecture that you want to be using in order to have a constellation and an architecture of relays in order to increase the achievable data rate. So that's where the solution comes in. There's multiple solutions, by the way. We're not going through all of them. There's multiple ways to do this, but we're really focusing on the heliocentric constellation because we believe it's the only one that can enable to achieve 100 megabit per second to the gigabit per second that we'll look at. It's the only one that allows you to have really small distance between relays, and also help whoever's manufacturing it benefit from economies of scale. So I mean, fundamentally, and then I'll just hand over to Julien again, but the idea in this heliocentric constellation is that you're going to be working with multiple types of orbit that are around the sun. So there's a lot of flexibility. You can use, circular rings on the right. You can use eccentric rings and orbits. You can use a combination of both. Here, for example, you see a ring of satellites that would be in the same orbit as Mars, a ring of satellites that's the same orbit as the Earth, and then like kind of what you would say a Omen transfer orbit, where you have satellites that are helping you make the connection between those two orbits. So here you have to imagine that you have a chain of satellites that are just passing data, neighbor to neighbor, and so on and so forth. So these are the few concepts that we need to kind of present the rest of the presentation. Important information. So if you're working the data in terms of the data flows tangentially or serially in a given ring on the same orbit, or it can also actually flow laterally. If you have to imagine that there's a lot of different links. Here we see them a little bit better, but you're going to see that this data is moving radially, hopping from ring to ring. And that's really, if we try to simplify as much as possible, that's really how the data flows in such an architecture. If you unwrap completely the constellation, and you imagine that you have your Earth ring, where you have your satellites, your Mars ring, where you have also satellites preceding and following the planet on the orbit, and potentially multiple in-between rings. If let's say you want to move them, let's say this is megabit per second from Earth, you can actually send half of the data, in front of you, behind of you on the satellite. You're going to get 5 megabits on each side, and then you're going to parallel, send the data parallel to the next ring, and then all the way to Mars, and do the process in the reverse way. So these are a few concepts that we needed to introduce so that it's easier to go through the next slides in the presentation. So Julien, up to you.
Thank you. So this is a video of the actual model. You can access it on a laptop. It's not optimized for smartphones, but if you use your computer screen, you can go to marslink.io, and here you can just see like it's moving fast, so the time is accelerated, and you have some sliders. So you can change the number of rings here. You can change the number of satellites within each ring, for example, which is what is happening here. So you can see the density of satellites gets greater and then lower as you move the little sliders here. There's really a bunch of things that you can do. Now I removed the circular rings and I put only eccentric rings, just to see the effect. And again, changing some of the parameters here. Now I put the spatial configuration, as you saw for a second, of the classic Hohmann transfer. So yeah, there's a bunch of things that you can do if you want to have fun designing your own Marslink constellation. Anyways, looking at those three larger design options again, I'm not going through each particular thing because we're going to be running out of time otherwise. But the classic Hohmann transfer is the cheapest one. It requires the least number of satellites, but it has only disadvantages. The latency is not good. The resilience to failure is not good, because if you have one failure here, anywhere, well, you lose half of your path, and then if you have one failure on the other side, you lose the other path. Essentially, you're out of path, so the entire speed gets downgraded very quickly. The launch opportunity is just once per year for this one. You have to be here to launch. And the in-transit spacecraft almost never see this ring because it's just one ring. The eccentric rings option is more of a hybrid, so it's a little bit better, but it's not much better, and it's 80% more expensive, so it doesn't really make sense. The best one though is the circular rings option, which is 27% more expensive than the base option, but the latency is great. It's 5 minutes if you're at the nearest point. If you're at the opposite point, it's only 30 minutes, although the data has to go all around the sun. It has the best resilience. Launch opportunities is every day, and the in-transit spacecraft see a satellite at any point in time during the transit from Earth to Mars. Okay, so let's look at the design for 1 gigabit per second. Tu veux faire ça là, du coup?
Okay.
Okay. So, yep.
Why was the eccentric one more expensive? Because it uses less satellites, or am I mistaken?
there's a bunch of satellites. The density is much more to reach the same bandwidth or the same throughput, and that's the reason. So before moving to the next slides and looking at in a little bit more detail, we need to talk about the laser technology improvements. The problem we have is we're not laser experts, and we don't know if SpaceX is going to build this. We don't know what laser they're going to take and what's their manufacturing capability. So we have to take some assumptions, and actually we have to do an analysis on different options. So based on their existing technology, which is the Starlink inter-satellite links, which is being used today on Starlink, they can increase or improve a lot of factors to get to a better performance. Of course, the cost will rise, but they will find a good trade-off between the performance and the cost. For example, this is the baseline here. It's 1x. TSAT is already at 70x. It costs more, of course, but it's possible. And Psyche, the mission that Matt mentioned earlier, is at 90,000x. So it's definitely technologically possible. It's just a lot more expensive. What is a good trade-off between performance and cost is for the industrial party to answer. Okay, now here's the table. This is a sensitivity analysis looking at the design for 1 gigabit per second. We took the worst case of a conjunction, which is, it happens to be 2034. This is where Mars is at the furthest on its actual orbit. So this is the worst case. We look here at different laser technology improvement factors. Again, 1x is the Starlink baseline from today, 100 gigabit per second over 5,400 kilometers. This is our baseline. This means 64 times better than this. And 256, 1,000, and 4,000. Without delving into too much detail, I highlighted in orange here all those options, all those configurations that are close enough to 1 gigabit per second. And here I'm just going to pick one as an example. This one here. This requires 6 concentric rings, 6 circular rings, and it requires 100 megabit per second between the satellites inside each ring. So the number of satellites within one ring depends on what megabit per second you want between each of those satellites. More megabit per second means more satellites. So this means 1,754 satellites in this entire constellation, and you get, let's say, 1 gigabit per second. But if your improvement is not 1,000, if it's only like 256, you can still get by, but you need more satellites, 4,200. So maybe it's better for the industrial party to pay more for the laser links, but then have less satellites. I'm moving a little bit fast on this one, but if you have any questions at the end, we can always come back. Now, this is the constellation that we selected, the one that I showed you as an example, with 1,700 satellites. This is exactly how it looks. And so this is the Earth right here. Mars is there. And when the links are white, it means they're not being used at the moment. When they're blue, it means they're being used at a small capacity. And when they're red, they're used at a high capacity. So it's not just a matter of taking one single line and getting to Mars. It's a matter of spreading, like getting all the capacity that's available. But there's a bit of an imbalance in this particular configuration, meaning we don't actually use all of the links. But if it's perfectly balanced, then you actually end up using almost all the links. Even if you have to go back and then, behind you and then come back to Mars. Because what you want to do is to have more gigabit per second, so use more links. Just to answer any question on the latency, if you are in opposition, which is when the two planets are closest together, the best you can get is around 6 minutes. The average is around 16 minutes, but the worst is actually around 25 to 30 minutes because the data has to take a long path to then come back to Mars. In conjunction, which is when the planets are really opposed, this is a different graph. It's really terrible latency. 30 minutes is the best, but this is how it is. You have to go around the sun. Okay, and then looking at the costs, I have just 3 slides on this. The technical summary is an option when you go to our website. By the way, this is just a free website. It's just a model. We did it for ourselves, but it's for free on the internet. And so you click a button, that's the deployment report, and it will tell you for each ring how many satellites are needed, how many laser terminals, how many Starship flights, how many tanker flights to refuel the Starships, and how much fuel is needed, how much argon, and how much methane and oxygen. So these are the technical totals, and that's the financial summary here. That's the same totals, but now in million of dollars. So this one costs 11.7 billion total, this constellation we just saw. And this is now the same table, but instead of seeing the number of satellites, we see the cost in billion of dollars. So again, this one we chose earlier, 11.7 billion. But if you chose that one, because your technology in the laser links is not as good as this technology here, then it's 28 billion. But if your technology is really excellent, 4,000 times the current technology, then you can get by with with 5 to 7 billion. Just in terms of the assumptions for these costs, a Starship or tanker launch is 20 million in our assumptions. The satellite is 5 million. One laser terminal, 200K. 4 terminals per satellite. And we did calculate the delta V requirements for the deployment. That's it. So a few key findings. So first of all, the circular rings are the best configurations, according to us. You can serve in-transit spacecraft. It's not just for the planets, but it is for the planets, of course. You need 4 laser ports per satellite, not just 3. Otherwise, you get only half of your throughput. There's a trade-off between the in-ring satellite count, so how many satellites in your ring, and how many rings you want to have. And as you saw earlier, we had a few white links, meaning that the trade-off was not perfect. There needs to be an improvement in the mass-manufactured laser technology. So SpaceX will probably do this at some point. And then you can have Marslink with 1 gigabit per second between 1,000 and 4,000 satellites. So this is really doable. I think this will happen sooner than later, I think. And the cost from 5 to 30 billion, according to our assumptions, which might be seen as reasonable for supporting a Martian colony. Thank you very much. Yeah.
First of all, this is awesome, really.
Thank you.
Second of all, I was wondering, you want to replace the defective satellites, and the new one should be in a very similar position as the old one, so you probably want to deorbit the old one. Will deorbiting old ones also be heliocentric? Will you deorbit them into the sun?
I think the energy required to do that is just tremendous, and so I think it's not possible. You just leave them in place, really. That's my best answer. And also, if you lose one satellite, you lose less than 1% of your bandwidth, of your data rate. So instead of having 1 gigabit per second, you have a 995. So it's not a big deal.
Right.
You didn't tell Musk about this, did you?
So the reason we did it is because Musk is planning this. But we just don't know what he's planning, and we're curious. So it's like, I want to know what he's doing. The same with Starlink a few years ago. Yeah.
I agree. This is awesome. Thank you.
Thanks a lot.
For the presentation.
Hey, you'll do it too.
I'm curious. Right now it sounds luxurious, a gigabit per second over at Mars when we have close to 0. But you're speaking about SpaceX's plans, and they talk about 1,000 Starships per launch window.
Yeah.
Not too far from now. Now you can argue about whether that will come true, but if it does, and you divide that total bandwidth across those ships in transit, now we're talking just a megabit per second per ship, and then you have 100 people on each ship, and they get 10 kilobits per second.
It's not a lot.
How does it scale? I guess I'm asking these questions about cost and such. If you went to 10 gigabits total bandwidth, 100.
Yeah, absolutely. So first of all, I don't think that each of the 1,000 Starship every 2 years will have people. Some of them will have cargo, but that's beside the point. How does it scale? Well, it's hard to scale, obviously. You have to improve your laser technology, and if you do that, you don't need to scale the number of satellites so much. I doubt that SpaceX will put like 10,000 satellites or 40,000 satellites. This is what they do around the Earth. But I'm sure if they can avoid doing that around the sun, they will, because the cost is really high. So I think they will focus more on the laser technology. And once you do, and if you play around with the simulation, and you play around with that number, actually, I should really do it just to give you an idea. It changes really significantly. So there's 4 rings as an example. Can you see this? Yeah. And that's the tech improvement factor, okay? So I'm going to 500. And now if it improves to like 32,000, you see the number of satellites decreased crazily. So if you want to increase your bandwidth here, you just say, well, you know what? I'm going to increase the number of rings. I'm going to increase the throughput. And now you're back with the original constellation almost. And now you get, here you have 5 gigabit per second right now. And so, but you will never get to like the terabits and things like that, according to our model, because the distances are just too large. I don't know. That's what our analysis shows at the moment.
Thank you.
Sure. Yep.
I want to ask almost the opposite question.
Okay.
Because if you think about what people use very high band links on Earth, it's things like video conferencing or high-end video games or even high-speed stock trading. So
Yeah.
things that are essentially real time. Now that's not possible with Mars because of, unfortunately, physics. So given that you will always have that unavoidable lag and the real time is impossible, what do you see as the use case for this level of bandwidth?
I don't know. Actually, I never asked myself this question. I just thought, wait, they want to do 1 gigabit per second? Really? How? And that's what but it's a fair question. But I think with the number of robots that will be operating on Mars, you need to tell these robots what to do. You need to see what those robots are doing and download the images. So that's already the first use case. And then if there's actual people on Mars, at some point they're going to want to send video messages to their loved ones back on Earth and vice versa. And that's another use case requiring video. Also, if you want to download Netflix movies, that's yet another use case. So I think over time it's like everything. If the resource is available, people tend to use it to its capacity. Yep.
I was curious because we're looking at the complexity of the relay system, but do you think there's going to be an associated increased complexity of the ground segment from both Earth and Mars to communicate through the system, and also of the way we're packaging the telemetry data to actually be able to, because essentially you're kind of splitting it up amongst different satellites. So to me that also sounds like a complex problem to solve, how you package the data so you actually get it back together.
Yeah. Yeah, we did not go into this detail. I think it's going to be something similar to either what the internet is doing today. When you send a request from the US going to Italy, well, the packages go their different ways and then come back. So a similar kind of protocol. And I'm sure that SpaceX has already implemented this for Starlink, but we haven't looked into detail. And when it comes to the ground infrastructure, which you mentioned earlier, we have decided not to model what happens at the Earth and on Mars, but just in between, because it's a little bit more trivial, and we didn't want to spend time doing that. But if you have already Starlink here and an equivalent on Mars of satellites orbiting those planets, then you just make links between the planet constellations and the heliocentric constellation, and you're golden, basically. But I know it's easy to say and very hard to do.
Thank you.
Yep.
Have you come across the work, in relative to Jane's question or remark, that of Professor Gunther Nims in Germany, University of Cologne, Professor Emeritus of solid state physics, who demonstrated an FTL communications device at the ISDC in Dallas, paid his way, because nobody else thought it would work, but it did. And he can exert a multiple of the speed of light using the undersized waveguide effects, using an effect called the Thomson effect, which is published by Texas Instruments in 1960.
Wow.
And so I asked, well, aren't there natural waveguides? You guys might know the answer to these questions, because natural waveguides could exert the same effect if you can get the relative frequency of the microwave transmission relative to the waveguide, because it acts as a funnel or a tunnel, right? And it also acts as an amplifier in the direction of transmission. So, and there are these currents going through space, Berkeley currents and Parker spiral in particular, that look like they exert waveguides or express waveguides. And it's kind of the idea, the old science fiction idea of subspace.
Mhm.
In fact, the title of his book is Zero Time Space.
Oh, cool.
Because it hops the interval across the waveguide without spending any time within the interval. And it's proportional, the speed of transmission is the inverse of the frequency.
Wow.
Okay?
I didn't know about this.
Yeah, and you wouldn't know about it because people in this country say, that doesn't work, we know that. But over in England, not in England, but in Germany, he's got patents on the devices.
Wow.
So far I know, he's made a fortune in high-speed trading already.
That's awesome. Thanks for sharing.
Yeah, NIMTZ, the name, NIMTZ.
Yeah, we'll have to look it up. Thank you very much.
Okay, just,
You had a question? Yep.
How do you make sure that the satellites stay where they are, especially the ones close to Earth and close to Mars? Will be affected by the gravity of those planets?
Yeah.
Will they have solar-powered thrusters or anything?
Yeah, that's a real concern. We have not looked into how to solve it. I can imagine right now what they would do, but my answer is going to be probably irrelevant. But I would just, if I was SpaceX, I would just, okay, let me just back up. Those satellites which are further out, they need more gas in their tanks to circularize their orbit, because in my model, the Starship only is used to put them on the trajectory to their orbit, and then the Starship comes back so it can be reused immediately. The satellites then go on the journey of, let's say, 6 months, or like whatever, to get to their furthest point, and then they circularize by themselves. So these satellites which are further out need more gas. Now, those closer to Earth could have as much gas as possible in their tanks, and thereby staying longer. But in a normal SpaceX way, I don't expect them to put satellites that will last 10 to 20 years. They're more in the 5 years kind of realm.
So isn't space then going to be littered with like
Yeah.
old ones? And
Yeah. But space, like, around Earth is already large. This is like unfathomable, like how large it is. So I'm not saying I'm in favor of or against it, or it's good or bad. There's some issues for sure, but I don't know.
Yeah, no, fair, yeah.
Cool. Thank you very much, guys.
So we need the immortal mitochondria.